Welcome to the presentation on cache memory design. In this session, we will explore cache organization and replacement policies, essential concepts in digital logic and design. So, what exactly is cache memory? Cache memory is a high-speed storage area that sits between the CPU, that is, the central processing unit, and the main memory. Its primary purpose is to store frequently accessed data and instructions, which helps to reduce the average time it takes for the CPU to access memory. Think of it as a quick access storage for the CPU. It reduces CPU wait time with its fast access. It has a small size, which means limited but strategic storage. The management of the cache is handled automatically by hardware. Let's delve into the memory hierarchy. We have three levels here. Level 1 cache, also known as L1 cache, Level 2 cache, also known as L2 cache, and main memory. Level 1 cache is the primary cache, the one closest to the CPU. It typically has a size of 8 to 64 kilobytes and a speed of 1 to 2 cycles. Level 2 cache is the secondary cache, which can be either shared or dedicated. Its size ranges from 256 kilobytes to 1 megabyte, and its speed is about 3 to 10 cycles. Finally, we have the main memory, which is the primary storage, or RAM, with a size of gigabytes to terabytes and a speed of 100 plus cycles. Now let's discuss the different types of cache organization. We will cover direct mapped, fully associative, and set associative caches. In a direct mapped cache, each memory block maps to exactly one cache line. In a fully associative cache, any memory block can be stored in any cache line. Set associative cache is a compromise between direct mapped and fully associative approaches. Some of the features of direct mapped cache are its simple implementation, fast access, and high conflict rate. Fully associative cache has features like no conflict misses, complex hardware, and expensive implementation. Set associative cache has features like reduced conflicts, moderate complexity, and is the most common design. Let's focus on direct mapped cache. In this type of cache, each memory block has a fixed location in the cache, which is determined by the modulo operation. The formula is cache line equals memory block modulus cache size. Some of its key characteristics are simple hardware implementation, fast cache lookup, and a low-cost solution. But it has a high conflict miss rate. Let's shift our focus to cache replacement policies. When the cache is full, a decision has to be made regarding which block should be replaced with new data. The different types of policies are least recently used, also known as LRU first in first out, also known as FIFO least frequently used, also known as LFU, and random. The least recently used policy replaces the block that hasn't been accessed for the longest time. The first in first out policy replaces the oldest block in the cache. The least frequently used policy replaces the block with the lowest access frequency. And the random policy replaces a randomly selected block from the cache. Let's discuss the least recently used, also known as LRU implementation. The steps for the algorithm are: first, find the least recently used block. Second, replace it with a new block. Finally, update the access time. Some of its key features are temporal locality exploitation and good performance for most programs. However, it has a complex hardware implementation and requires timestamp tracking. Let's explore cache performance and summarize our discussion. The performance metrics include hit ratio, which equals cache hits divided by total accesses, and average access time, which equals hit time plus miss rate times miss penalty. Some of the design factors are cache size, associativity, block size, and replacement policy. Cache design involves balancing performance, cost, and complexity to optimize memory hierarchy efficiency. If you like this video, hit that like button and don't forget to subscribe. Visit CodeLucky.com for more such useful content.